Hi folks, welcome to Astronomy Live. In this video, we will be discussing stellar parallax as a method for finding the distances to stars and whether or not negative parallax refutes the use of this method for finding stellar distances. First, let's talk about the principle of how we can use stellar parallax to infer the distances to stars. In this diagram, we have a collection of red stars at a greater distance than this bright blue star to the white circle representing Earth's orbit around the yellow star representing our Sun. Of course, this diagram is not intended to be to scale. In reality, the angles measured for the parallax of even the closest stars are incredibly tiny, as we'll discuss later. And so, in order to better illustrate what's going on in this diagram, the distances between the stars and our solar system have been brought down to a scale where we can more easily see what's going on. Now I will project green lines representing each parallax observation 6 months apart on opposite sides of Earth's orbit to the target star and extending beyond to the red field of more distant stars in the background. This represents a case where we would see a positive parallax value, with the first green line projecting to a spot on the background stars to the right, and the second green line projecting to a spot on the background stars to the left. So if we put the camera where Earth is at each of those 2 points, we see the star appearing to move from the right to the left relative to the background stars if we use those background stars as fixed points. Now, lately, flat earthers have been claiming that about half of all stars surveyed for parallax actually come back with a negative angle. The exact percentage varies depending on who you ask, but in general, roughly half, they say, actually have a negative parallax angle. So how can that possibly be? Let's take a closer look at where they're even getting that figure from, and what the potential explanations are, and what their particular claim is regarding negative parallax. The paper that CryptoKeys cites here from 1943 actually gives a variety of explanations for why negative parallax can occur, and we'll go over those explanations in just a moment. But CryptoKeys would like to disregard all of those explanations in favor of his preferred possibility, the idea that Earth is stationary and it's actually the stars doing the moving, which is why about half of them move the wrong way, he thinks. Well, if that's true, it makes a prediction about what we should see over this last century as we continue to survey those same stars with better and better instruments over time. We should continue to see the same percentage of those stars exhibiting negative parallax, even as those same stars are resurveyed with better and better instruments with greater and greater degrees of precision. So, we will take a look in this video as to whether or not that's actually occurring. Now let's take a look at the various reasons why negative parallax can occur according to the paper cited by CryptoKeys, which he highlighted in this screenshot. The first reason given is that if the parallax of the star is smaller than the measurement error, it is possible for the measured value of the parallax to actually come out as negative, simply due to the measurement error, but this does not reflect the real parallax of the star. Measurement error is inherent in all measurements, and if we take a look at these ice cubes, we know for a fact that they are actually colder than 0 degrees Celsius. But if I take an infrared thermometer and point it at the ice cubes, we can see that the value measured actually fluctuates on either side of 0 degrees Celsius. Of course, it doesn't mean that the ice cube's real temperature is fluctuating to this extent. This is simply measurement error in action. If a star's true parallax angle is significantly smaller than the precision and resolution of the instrument being used to measure it, then you essentially have an equal chance of ending up with either a positive or negative number due to measurement error. This can account for a large number of stars with negative parallax that is very close to 0 in any given catalog. In this particular case, the paper is citing Schlesinger's Catalogue from 1924. I could not find a digital version of this catalog except for the e-book of the catalog itself, so I've taken the liberty of manually transcribing the modern identities of the stars from that catalog with negative parallax in that catalog, using the coordinates listed and accounting for precession over the last 100 years. I will include links both to the original e-book of this catalog as well as my transcription of the negative parallax stars from that catalog, along with their modern identities and more recent measurements of their parallax, and you can find links to those in the video description. But before we take a more in-depth look at negative parallax in the catalogs cited by CryptoKeys, let's first take another look at the other reasons that his own paper mentions for possible negative parallax appearing. The second reason given for negative parallax to occur is due to double stars. Double stars that are visually close to each other may actually be merged at times due to atmospheric seeing. Atmospheric seeing refers to how atmospheric turbulence affects the image quality in a telescope, and if the seeing is bad, it can even cause stars to appear to merge. In this time-lapse, you can see a Falcon 9 second stage passing by a star under poor seeing conditions, and this actually causes the star to appear to merge with the trail of the Falcon 9 second stage, causing it to look bent as it passes the star, confounding our ability to precisely measure the position of either one. Of course, atmospheric conditions are only a problem for measurements made from the ground, as was the case when Schlesinger made his catalogue of parallaxes 100 years ago. But with more modern space telescopes, we can at least eliminate that as a factor. But even space telescopes have to contend with the fact that some stars are physically close to each other, and these binary stars orbit each other over time, which causes their positions to change, and this can actually produce negative parallax in some cases. Let's first refresh our memory on the normal situation where we have a star closer than the reference stars, and observations made 6 months apart intersect at the point where that star is located. But now let's imagine that this is not a single star, but instead a binary, and it's orbiting a smaller but more massive star like a neutron star. Once again, we make measurements 6 months apart, but now the sightlines intersect at a point beyond the field of background stars. This is an example of negative parallax. The motion of binary stars is not the only motion that can impact parallax measurements. Proper motion can also impact those measurements, and even Schlesinger's catalogue from 100 years ago attempts to correct for this, and does list the proper motion of each star in the catalogue. As with the measurement of parallax, the measurement for proper motion also has its own error, and this is dictated not only by the precision of the instrument, but the period of time for which we have observations. For example, I took these pictures of Barnard's star 5 years apart with my telescope, and you can easily see the proper motion that is occurring between those photos. However, if I had taken photos only 5 days apart, it's unlikely you would perceive any motion in that short period of time. So if we do not have a good determination of the star's proper motion, or if there's a large amount of error or uncertainty, it's possible for the proper motion of the star to actually contaminate the signal of its parallax and even produce negative parallax. Here's a diagram to provide an example. Once again, the star is observed 6 months apart, but because the star is moving, if this is not accounted for, the sightlines intersect behind the background reference stars, producing negative parallax. Given the points of observation in this diagram, we would expect to see the star appear to move from right to left relative to the background stars if we were observing positive parallax. But in this situation, because the sightlines converge behind these background reference stars, the star appears to move from left to right relative to those reference stars. Because we're measuring parallax relative to other stars that we assume are in the background, generally because they're fainter, if it turns out that those stars are actually intrinsically faint and closer than the star that we're measuring, this can also produce negative parallax. Once again, we have a bright blue star that we're measuring using observations 6 months apart, and once again we find that the sightlines intersect behind the reference stars, producing negative parallax. In this case, the negative parallax value can be quite large because it's not due to small amounts of measurement error that happen to produce a negative number, and it's also not due to small amounts of motion of a binary star or small amounts of improperly measured proper motion. If we had a more complete survey of stellar distances, including close dim stars and intrinsically bright distant stars, we could better work out which ones are truly in the foreground and which ones are truly in the background. The catalogue of stellar parallaxes cited by this paper is 100 years old at this point, and they didn't have the benefit of those modern advances or more complete surveys to build upon. So it's rather remarkable when you look at this that there's relatively few negative parallax values in the table. Of the 1,870 objects listed in this catalog, only 194, or about 10%, have negative trigonometric parallax values. As I mentioned earlier, I looked up the modern designation and used Simbad to find a more recent parallax measurement for every object listed with negative parallax in this catalog. The parallax values from the Simbad database are reported in milliarcseconds. 1 milliarcsecond is equal to 1/3,600,000th of a degree. These measurements generally come from either the Hipparcos satellite or the Gaia satellite, and we'll be talking more about those missions in just a moment. Looking through the entire list of objects with negative parallax in the Schlesinger catalog, we find a couple of items whose parallax is statistically no different from zero, but we find no examples of negative parallax when comparing it in the Simbad database. This spreadsheet and all other spreadsheets I present in this video are available as links in the video description below. Next, let's talk about the Hipparcos mission. This satellite was launched in 1989 by the European Space Agency with a mission to map the stars. Its main instrument cataloged over 118,000 stars, complete down to the magnitudes that we can see by naked eye. So every star that you can see at night with your naked eye, even under pristine conditions, was mapped by the main instrument of this satellite, measuring its precise position, proper motion, and parallax. Additionally, there was a less accurate instrument on this satellite that was used to map 1,000,000 stars, but with 20 times less precision. First, let's talk about the main Hipparcos dataset, which contained about 118,000 stars cataloged by the main instrument. Out of those stars, about 4,196 came back with negative parallax, or about 3.5%. Already, that's a lower figure than the percentage of negative parallax that we had in the older Schlesinger catalog, and this Hipparcos catalog covers many times more stars. Just as we did with the Schlesinger catalog, we can compare the results from the Hipparcos main catalog to a more recent and more extensive and higher precision survey conducted by a more recent spacecraft, the Gaia spacecraft. Gaia was launched to the L2 Lagrange point in 2013, and in 2014, while they were performing testing and turning its sun shield towards Earth, I spotted it in this time-lapse. Gaia is more accurate than even the main instrument for the Hipparcos mission, and it is surveying vastly more stars, even more than the less accurate instrument for the Tycho catalog. If the flat Earth claim is true, then if we look back over the stars previously surveyed by the Hipparcos mission and look at the stars that exhibited negative parallax, then even if we're using a more precise instrument like Gaia, we should continue to see a stable percentage of stars continuing to exhibit negative parallax out of that original Hipparcos catalog. Unfortunately for the flat earthers, when we look up the stars that had negative parallax in the original Hipparcos catalog and find them in the Gaia DR3 data release, we find that 99.5% of them now have positive parallax. And of the 0.5% that continue to show negative parallax in the DR3 data release, their standard error is 4 times larger than the stars that now have positive parallax, indicating that it is simply measurement error. But if we look back at the original Hipparcos catalog, let's remind ourselves that only about 4,000 stars out of that 118,000 star catalog actually showed negative parallax to begin with, or about 3.5%. So where does the figure come from that the flat earthers keep quoting, that half of all stars show negative parallax? Well, it seems that figure comes from the 20 times less accurate and now obsolete Tycho 1 catalog. Remember, there was another instrument on the Hipparcos satellite that was also mapping the stars. In fact, it was mapping about 1,000,000 stars, but doing so with 20 times less precision. While CryptoKeys' fourth possibility predicts that we should see a consistent percentage of negative parallax despite increases in an instrument's precision, in reality, it's not surprising that as an instrument's precision decreases, and as it surveys an even wider swath of even dimmer stars, that the percentage of negative parallax increases to the point that it is almost the same as chance, or about 50% simply due to measurement error under this less precise instrument. But let's take a listen to what the flat earthers claim about this particular catalog.
Took 1,058,332 observations of stars. Over a million. Okay, so I want to put that number, a million. This is not just, okay, we took 10 pictures or something. No, a million objects that they accounted for. Peep this, y'all. Out of this million, 262,000 records of negative parallax.
Astronomy Live cutting in here, and just to avoid confusion, the page that he's reading from is published by a geocentrist, someone who literally thinks that Earth is the center of the universe, but that it is at least round. So, a different flavor of conspiracy theorist, but perhaps less wrong than a flat earther. And this geocentrist is admitting that the values that are very close to zero are statistically truly no different from zero, but CryptoKeys wants to disregard all of the three explanations that we covered earlier in favor of his preferred fourth explanation, so he wants the complete figure of negative parallax stars in that database. He gets to what is almost the right answer, but for the wrong reasons, as we'll hear in a second.
262. Now, mind you, this is coming from the European Space Agency, which is strange because you would think that other space agencies would have like some of this data as well. And I couldn't find it.
For some reason, flat earthers tend to act like NASA is the only space agency, and they act surprised when missions are conducted by other space agencies. There's really no reason for NASA to redo the Hipparcos or Gaia missions. ESA has it pretty well covered.
You know, this guy kind of highlights in this paper. I think I linked the thread here so you could, kind of go through the paper yourself. For some reason, the ESA was the only agency to kind of have some of this information. So that was super strange. But out of 1,262,000 records based off of like a specific parameter, all had stars moving in the wrong direction. It doesn't end there. This paper then says, next we selected positive parallax objects. And they give certain values. With these positive parallax objects, they also recognize 310,000 records of negative parallax.
Okay, that's not what that page said at all. He got that completely wrong. He just took the figure for the stars that page says have significant positive parallax, and he just called them negative parallax stars. That's dead wrong. Now, despite completely misinterpreting that part of the page and getting it totally wrong, by sheer luck he actually lands on a percentage that's not far off of the correct value. In reality, out of the 1,058,332 stars in the TICO 1 catalog, about 453,734 have some amount of negative parallax, and that comes out to a percentage of about 42.9%. Once again, unlike the geocentrist who created this webpage, CryptoKeys doesn't accept any of the previous explanations that we covered for why negative parallax can occur. In fact, he spent a good bit of time expressing his own personal incredulity at the explanations offered by that previous paper. He prefers his fourth possibility, that negative parallax is actually the real motion of the stars, and so increasing the instrument precision shouldn't change the percentage of stars exhibiting negative parallax. In order to test his claim, I wrote a program in Python to query the massive Gaia DR3 data release for all 453,734 stars that exhibited negative parallax in the original TICO 1 dataset. It took my computer running about a week solid day and night to find the matching entries in Gaia DR3 for each of the 453,000 stars that showed negative parallax in the original TICO 1 dataset. But it's finally done, so let's take a look at the results. Here's the results of my program, and it's not good news, either for the flat earther or the geocentrist for that matter. Do you see all the negative parallax values scrolling by on the TICO 1 parallax column? And now if you look just to the right of that, you can see all the positive values scrolling by on the Gaia DR3 parallax column. For the stars with a negative parallax value in the TICO 1 catalog, that have a corresponding parallax value available in the Gaia DR3 data release, 99.85% now have a positive parallax value. For the 0.15% of stars that still have a negative parallax, according to Gaia DR3, those stars have a standard error of their parallax measurements that is 13.7 times greater than the average standard error of parallax measurements throughout this entire list. So while measurement uncertainty and measurement error can contribute to negative parallax, as instrument precision increases over time, when we look back at those same stars again, we find that they resolve into positive parallax values. This result directly contradicts the prediction made by the flat Earth claim being addressed in this video. They may try to retreat into the fraction of a percent of negative parallax that persists when the TICO-1 dataset is reanalyzed using Gaia DR3, but this video demonstrates that as our instruments increase in precision over time and as we develop more comprehensive datasets at these increased levels of precision, what we previously measured to be negative parallax resolves into positive parallax. So if you see any flat earthers claiming that half of all stars show negative parallax, or half of stars go the wrong way when we measure their parallax, be sure to point them back to this video, because that statistic comes from the outdated TICO-1 dataset, and when we look at Gaia DR3, those same stars that showed negative parallax in TICO-1 turn out to show positive parallax 99.85% of the time. Thanks for watching, and until next time, clear skies.